So today we continue the previous topic of electrostatic potential, okay, and potential energy, okay. So here previous class we end here potential at point P and electric field at point P, okay. So both are same. So difference is that is one is the inversely proportional of R and potential is inversely proportional of R and electric field is inversely proportional of 1 by R square. Okay, so the energy of this case, energy W equal to, that is Q small q over 4 pi epsilon naught R, that is joule. That is energy equal to capital Q source charge produce electric field and potential, and that is a test charge. This test charge bring infinite to a finite point if I work done by external force actually. That is a joule energy, that is 1 over R, okay, and that is equal to potential at point P, that is equal to know that W by test charge Q. So that is we get equal to Q over 4 pi epsilon naught R. So cancel these Q and these Q, okay. That is a potential, that is a joule per coulomb, and joule per coulomb we know that that is a volt. So Q over 4 pi epsilon naught R volt. That potential at point P, that is very important, potential at point P, that's not a potential energy, that is potential at point P. Both are scalar, okay, that is a potential at point P, that is scalar quantity. And what is the potential and potential energy related? So potential at point P, that is equal to, for bring a charge from infinite to a finite point, that is actually a change in potential energy, delta U by test charge Q. So delta U means bring a charge, test charge, actually infinite to any finite point. So here infinite to finite point, there is a final potential energy minus initial potential energy by test charge Q. So know the final potential energy is infinite to a finite point. So U infinite minus U at point P by Q. Okay, so we know that potential energy at infinite, that is equal to 0 joule. That is a reference configuration, okay. So we discussed previous class what is the reference configuration, how to calculate the potential energy in suppose example a gravitational potential energy calculation. So that is equal to 0. Sorry. There is a difference actually. Sorry. So final at point P, that is a infinite. Bring a test charge infinite to finite point. Okay. So let's look like this. A test charge at a source charge a capital Q, some distance here at point P. We bring a test charge infinite to at here. External force we apply from infinite to point P. That's the initial, that's the final. Okay. So final minus initial, okay, that is equal to 0. So that's why we get UP over Q. That's actually delta U. So delta U we get, that is equal to Q times Vp, potential at point P. And here the motion, if I charge from infinite to a finite point, so if I charge bring back, so there is a motion actually. So this motion, box that equation, and here the motion through the electric field. So that's the motion for test charge. So test charge they have movement, okay. So movement test from infinite to a finite point, okay. So work done by the field. So now calculate work done by the field. So work done by the field. So see the diagram very carefully. We bring a test charge and a positive test charge, very small amount, two charge configuration. So if that is a positive, source charge also a positive, so there is a repulsive force actually. So that electrostatic force is a repulsive force. Okay, so electrostatic force is the repulsive force, that is a minus of F external force, or vice versa. That is a Newton's third law. There is a equal in magnitude, but they are in opposite direction. Okay, so work done by the field is, that is a W. So here you see that by the field, so charge moving from point P to infinite, okay. Suppose like that, if a test charge I release here, and there's due to the force, this is a actually these electrostatic forces push the charge and throw that charge from point P to far away from like infinite distance. Okay. So here we see that the charge moving infinite to suppose to finite finite to infinite point P to infinite. So potential at infinite minus final minus initial at point P, change in energy, that is equal to delta U. We know that for conservative forces we know that is independent of path electrostatic force. Okay, so that's why we get a minus term, get a minus delta U. If we compensate these two, get a minus delta U. So that is for minus delta U we get, okay, that is a U infinite minus a UP, and you know the infinite that is equal to 0. So minus minus plus, that is a UP, and UP potential energy at point P. Suppose in case of like delta U is the suppose that is a UP. Suppose here that is a UP, that is equal to Q times Vp. The UP that is equal to Q Vp, that is equal to W. You get another expression. Now we discuss important the conservation of energy. Energy neither created nor destroyed. You know that definition, okay, from class basic class 6, 7, you know that, okay. So definition of conservation of energy. So here case of conservation of energy, energy concept like that. So energy neither created nor destroyed, okay. So when a charged particle move in an electric field, okay. So here a charged particle, this is a test charge, these test charge move in an electric field. So electrostatic force and electric field both are in actually same direction. Electric field is a vector field, okay. So energy say that when a charged particle, moved in electric field, so only electrostatic force is applied. So only electrostatic force is applied. So source charge is fixed at a point, okay, here. So if electrostatic force is applied, you know that conservation of energy means before some event, that is a initial potential energy plus initial kinetic energy, that is equal to final potential energy plus final kinetic energy. Okay, so get a K initial minus Kf, that is equal to U final minus Ui, that is a delta K minus, that is equal to delta U, or say that delta K equal to minus delta U. And so delta U, we know that what is the value of delta U from here, that is equal to Q Vp, that is equal to minus Q Vp potential at point P. And what is the Vp from electric field? Very important, from electric field concept. So Q final potential energy minus initial potential energy at point P. Okay, so that is equal to delta K here. Next we discuss work by an applied force. Here for conservation energy, now we discuss work by an applied force. By an applied force. In case of applied force, so we know that suppose before an event, initial energy, potential energy plus initial kinetic energy, here some applied external force that is equal to final potential energy plus final kinetic energy. Suppose now we convert the Ki minus Kf, that is equal to Uf minus Ui, or that is a minus W applied. So delta K minus sign, that is delta U minus W applied. So I get delta K, that is equal to W applied minus delta U. I know the delta U, that is QVP. So delta K, that is equal to W applied minus QVP, potential at point P. Suppose the particle is at stationary. Suppose say that particle is at rest or stationary. So that is velocity equal to 0. If velocity equal to 0, means delta K obviously equal to 0 because K equal to half mv square. So that is equal to 0 equal to W applied minus QVP. That is W applied equal to QVP. Okay. When particle is at rest. But we know that, no, W that is equal to minus delta U. We know that. And that is delta U that is equal to QVP. Now replace QVP that is equal to minus W. So we get W applied equal to minus W. That's here these significance show that its work by the applied force is negative. So the work by the applied force is negative for the work done by the field. For the work done by the field. Okay. Now we clear the concept about what is the potential energy and what is the related between potential energy with work done, and also we clear the concept about what is the electrostatic potential. Okay. So concept about the potential at point P. Now we discuss another important point, calculation actually, is about potential due to a point charge. So we calculate potential due to a point charge. Potential due to a point charge. Okay, potential due to a point charge. So we know that suppose that is a plus Q, that is a source charge, and that plus Q produces electric field and also produce a potential. Now calculate potential at point P, and here that point P lies, suppose here, that point P. Okay, and bring a test charge from infinite to a point P. Okay, from infinite to a point P. So we choose an arbitrary point here. Okay, bring infinite to point P. So here that is work done by the charge on external force actually. External force, that is F external, that is infinite to point P, and that distance is R. The distance is small r to there. Okay, that is a dr vector. That is a dr vector. Now the distance is from here to that point is arbitrary point, that is equal to capital R. Choose any arbitrary point here. Okay, so being a test charge, you know that test charge is a positive charge. Okay, very small amount. Okay, compared than the source charge, because that is two charge system. If I choose suppose a huge value or approximate almost equal to the source charge value for test charge, so there is a orientation mismatch of the orientation. Okay, so that's why you choose a very small amount of test charge, means suppose 1 microcoulomb, if that is a suppose that is called 1 coulomb. Okay, that is a 10 to the minus 6 difference, not a minus 6, sorry, plus 6 order difference. Okay, source charge and test charge. So that's why this orientation is not disturbed actually. So the force, electrostatic force in that direction, because that is repulsive force. That force is a repulsive force because test charge is the positive and source charge is the positive. So that's why there is a repulsive force actually. Now we calculate the work done. So work done, so being a test charge from infinite to point P. From infinite to point P, suppose we choose a same value is R, choose any value actually, that is at point P. So bring a test charge from infinite to R distance actually. That is equal to external force dot dr. Now that the external force is minus infinite to R, that is electrostatic force, because from Newton's third law the magnitude of external force and electrostatic force are equal, but they are in opposite direction. Dot dr. Now change the limit, so R to infinite, that is F electrostatic dot dr, and that dr and FEL electrostatic force both are in same direction. If both are in same direction, that is suppose here that is A dot B vector, both are in same direction, dot product. So AP cos theta, theta is the angle between A and B vector. So similarly we calculate that electrostatic force, suppose same direction, that is equal to R to infinite F electrostatic dr. And you know that that is electrostatic force is Coulomb force from R to infinite, that is equal to from R to infinite, that is source charge Q small q test charge by 4 pi epsilon naught R square dr. Okay, so q small q by 4 pi epsilon naught with a common R to infinite dr by R square, and you know that capital Q test charge by 4 pi epsilon naught, so that is integration is minus 1 over R, so the limit put R to infinite. Suppose we put the value actually get work done, bring a test charge from infinite to a finite point P, so we get capital Q times test charge, that 4 pi epsilon naught. So actually capital Q times small q 4 pi epsilon naught, so minus 1 by infinite, minus minus plus, 1 over r. So 1 by infinite, that is equal to 0. So ignore that, is times r. That's the work done. I bring a test charge from infinite to finite point. Okay. And if I suppose I release a test charge from here, actually here, suppose then this test charge swept away actually, because there is a repulsive force. That's why test charge I bring here and release my hand, then test charge swept away from r to that infinity. So throw that from long distance here actually. So that's why W infinite to P, that is Q source charge Q by R. And you know that W at infinite to P by test charge, that is equal to potential at point P, that is capital Q over 4 pi epsilon naught R. So here the potential P at R, and potential is a scalar quantity, so it is a volt or joule per coulomb. That you know that. That's a potential. Okay. So here we see the very carefully. The potential is another relationship between that is called electric field. Okay. See that. Suppose electric field and potential, there is some relation actually. Previous class we discussed here. Yeah. So potential at point where the Q over 4 pi epsilon naught R volt, and the electric field is Q over 4 pi epsilon naught R square. So difference is 1 by R and 1 by R square. Okay, that's important. If a test charge consider, if we consider test charge, so some condition applied. Note that the test charge is 1 coulomb. Suppose the test charge, suppose consider the 1 coulomb, very small amount. So potential at point P R, that is Q over 4 pi epsilon naught R, that is potential at point P as is independent of test charge. Okay. But here I multiply the test charge as 1 coulomb, so they cancel to each other. Okay, that is independent of test charge. That is the independent of test charge. Potential at point P. Suppose Q, the source charge is greater than 0 with a positive, so the potential also the positive greater than 0. Okay, and if the Q is less than 0, the negative, so potential also the negative, that reaction actually. So work done by the external force, so work done by the external force is work done by the external force, bring a unit positive charge, bring a unit positive charge from infinite to finite point, from infinite to finite point. Okay, that means a negative work done from infinite to finite point. Okay, and work done by the electrostatic force. So, and another point, work done by the electrostatic force, by the electrostatic force, static force, bring a test charge from infinite to finite point, bring a test charge from infinite to finite point. So here the external force is negative work done, Electrostatic force is the positive work done. Okay. So if a test charge, suppose Q, source charge is a positive and Q is greater than 0, means positive, so there is a repulsive. If both case Q greater than 0, is a repulsive force. And Q also greater than 0, but test charge is less than 0, that is attractive force. Okay. Now if I draw a graph of potential versus R, so because the capital Q source charge is the constant and 4 pi epsilon naught there is also a constant. Okay. So draw a graph potential versus R. We see that this graph is now look like this. Okay. But same graph we plot electric field versus R. Now say look like this. Okay. At some point there is same potential. At some point there is a potential and electric field be the same. That point. If R is more, that red color represent electric field and gray color represent potential. So if R is more, you see that very carefully. So electric field is less, potential is more. But here if R is less, so electric field is some these values are more than potential actually. Okay. So here the graph represent actually the potential inversely proportional of R and electric field is also inversely proportional of R. Okay, and you know that suppose the potential that is equal to Q over 4 pi epsilon naught R, and here the electric field is E that is equal to Q over 4 pi epsilon naught R square. Okay, both are independent of test charge. Okay, so that's why now put some little bit change here. If I change Q over 4 pi epsilon naught R times R, that is the potential at point P, that is V by R, that is equal to E. And you know that electric field is a vector field and R is the displacement vector. So in vector notation we see that V, that is a scalar quantity potential, electric field is a vector dot R, so that the dot product. So that is dV equal to E dot dr. Okay. Suppose you consider this is suppose a sphere. Okay, and that is a charge placed on here surface. Surface. Okay, charge placed on surface, and that is a center point. Suppose that is a O. Okay, and point electric potential at here, and calculate a potential at that point here. Here the inside a sphere, at that point electric field is 0. Okay, inside that point electric field is a 0, and that point P, potential at PP. Electric field inside is 0. Suppose if electric field inside 0, that is dV by dr, at that equation actually, that is equal to 0. So dV equal to 0 dr. So integrate, that is integration of 0, we get a constant. Okay, 0 integration we get a constant potential. So inside that sphere we get a constant potential, some potential value here, same as potential value at here, same as potential value at here, same as potential value at here. Okay, so if I draw a graph actually, another graph for better understanding, that is a suppose potential, and that is a subdistance is that is called R. R, like that point, that is radius is suppose radius is a capital R. Suppose then R equal to capital R. At that point, after that point, and before that point, the potential is constant. Potential is the constant value. At here, the potential is constant. Okay, here the potential is constant, but after outside the sphere, this potential is inversely proportional of 1 by R. That is proportional to of 1 by R. Okay, so inside the sphere, potential is constant at any point inside the sphere. The value is a potential. Suppose here it is 10 volt. Here the potential is 10 volt. Here the also potential 10 volt. Here also potential is a 10 volt. But inside the sphere, electric field is 0. Okay, so suppose similar concept. You calculate potential at point P, Vp. Okay, so we know that bring a test charge from infinite to finite point. Similar concept, we calculate a sphere. So test charge here, bring a point test charge from infinite to any point here. Now we calculate suppose that potential, same condition actually potential at point P. So potential at point P, suppose function of R. So bring a test charge from infinite to finite point or against the electric field. Okay, so that is R2 infinite distance from R2 infinite. I know that potential that is equal to E dot dr. Okay, so E dot dr means actually you know that electrostatic force by test charge. So dr, that is a E actually. That term represents electric field E. And these E dot dr and electric field, obviously electric field in same direction E. So we just easily Vp of R to infinite. Suppose we get a electric field that is Q over 4 pi epsilon naught R square dr, because the electric field and dr in are the same direction in case of previous like this. So both are in same direction, dr and electrical both are in same direction, so AB cos theta, so theta is a 0 degree. Okay, the same angle between these two, so we get so similar condition Q over 4 pi epsilon naught, so R to infinite, so dr by R square. If I solve this, 4 pi epsilon naught minus 1 by R, so limit put R to infinite, we get Q over 4 pi epsilon naught. 1 by infinity is 0, so 1 by R. So potential at point P, function of R, that is Q over 4 pi epsilon naught R. So here is the important formula you get, the potential at point P, very important. And another relation between potential and electric field. Okay, that's the important formula relation. It is very important. This formula. The potential is a scalar and electric field is a vector and displacement also a vector. That's why if I dot product between these two, we get a potential at point P. Electric field at point P, we get a potential at point P. I know that potential is a scalar quantity. Clear the concept? What is the potential at point P and how is it related between electric field and suppose that there is a unit, obviously that's a volt. Okay, potential at point charge. Okay, so that the potential due to a point charge means those are actually, these are the concentrated sphere. Actually these behave as a point charge. If I these are point charge means actually this R is much less than of R, so these also behave like a point charge actually. Okay, clear? point charge concept. So I think now we clear the all doubts actually potential at point P and what is the electrostatic potential and what is electric field and relation between these two. If any doubt in further doubt, ask in comment section. I will try to give the answer. Okay. Next class we discuss calculate potential due to electric dipole and potential due to a system of charge and some concept of recall this class also. Okay. So today end the class here. Thank you.